So today we're looking at finding derivatives and integrals with exponential functions in them, specifically those with base of e. Next Tuesday we will look at exponential functions that have different bases, but today we're looking at base e. So first, before we differentiate, integrate, some basic things about exponential functions, things to recall: that they are inverses of logs. So if you recall, our log that has that base of e would be the natural log. So if our function was just the natural log of x and we were trying to figure out the inverse, then we would be switching the x and the y. And then in order to get it back where it's resolved for y, I would have to rewrite it in exponential form where I have my base of e raised to the x equals y. So this would be the inverse here, equals e to the x. So just knowing that our logs and exponentials are inverses of each other, that might come into play. Knowing what they look like is helpful. So our exponential is going to look something like this, and this is just our parent function, e to the x. It might be important that it's continuous, that it is differentiable, it is monotonic. So we just learned this word. It is monotonic because it is increasing for all values from negative infinity to infinity. So it might be important just knowing what it looks like, the fact that the limit as x approaches 0 is going to be 1. As long as we haven't added or subtracted to our exponential, we're always got that e to the 0 power is going to be 1, or any base really. And then also just knowing what it looks like, that my limit as x approaches infinity is going to be infinity. So as we go, our x's go to infinity, our y's are going to go to infinity as well. As our x's go to negative infinity, what's going to happen with f of x? As x goes to negative infinity, our y values are going to get closer and closer to 0. So just values that come straight from that graph, but might be helpful. Some other properties that might come into play, and we talked about these a little bit with logs because they are inverses of exponentials, so they act quite a bit the same. But just knowing that if I have e raised to the a times e raised to the b, that if I'm combining these, or more likely I'm expanding them, but if I'm combining them, then that means I'm adding a and b. If I have a similar situation, but I have division, that means that I'm subtracting a and b. And there might be a situation where we have the condensed form. Maybe we're trying to take the derivative, but it's easier to expand them and then take the derivative of both, or same thing with integrals. So beginning with derivatives, this is pretty interesting that the derivative of e to the x is actually e to the x. Nothing happens with it. If you think about what that graph looked like, and what would be happening with the derivative, we have a derivative here, our slope is close to 0, but our function is also close to 0. And then as the function gets further away from 0, it becomes steeper. So it just so happens that the same y value is actually also the derivative. So that means that my slope here at 0, since the y value is 1, the derivative there, the slope, is also 1. Very interesting. However, just like logs, if I have a base of e, but my exponent is more complicated, so I'm going to go ahead and say e to the u, then I'm still going to have e to the u for my derivative, but I'm going to have to multiply it by the derivative of u, so times u prime. So it's kind of that chain rule coming into effect, where here I had e to the x and then technically times the derivative of x, but that's just 1. Whereas if I have an exponent that's not just x, I do have to go ahead and multiply by the derivative. So for example 1, if we just have a simple exponential like this, it is really just as simple as following that rule right there, that I'm going to have my e to the 2x, but then times the derivative of 2x. So using that chain rule, and I'm just going to have 2 e to the 2x. On example 2, we've combined our natural logs and our e to the 2x. We've got both of those in there. So first, I would need to remember that to find the derivative of a natural log, that I'm taking the derivative of that argument over the argument. So when I take the derivative of the argument, my derivative of 1 is 0, but then that derivative of e to the 2x, we just did that, is going to be my derivative of 2x times e to the 2x. And then it's going to be all over that argument. So using both of them. And there's not really a way that I can simplify this. Nothing that I can factor out and cancel. So that's it there. For example 3, what rule are we going to have to use here? An oldie but a goodie. I'm having to use the quotient rule because we are dividing. If there's any way that we could simplify this beforehand, then we would, but there's not anything that I can do easily to simplify that. So we're using the quotient rule. I've got my derivative of the numerator, which is 2, times my denominator, minus the derivative of my denominator. So I'm going to have that e to the 4x plus 1 times the derivative of 4x plus 1 times the numerator. And it's going to be all over my denominator squared. Okay. And remember, for something like this, we don't necessarily have to simplify it that much at all. Something that you might notice is that we can factor out an e to the 4x plus 1 out of both of these, and that's going to allow us to cancel 1 down here. Since that derivative was the same thing, we ended up with it in both places. So an easy thing that we can do to simplify, factoring out that e to the 4x plus 1, it's going to leave me with a 2 in this left side. On the right side, I'm going to have minus a 4, 3 plus 2x. And then I've got it all over that e to the 4x plus 1. I've got 2 of them. So we're looking at being able to cancel one of the one in the numerator and then one of them in the denominator. Again, if we want to keep going, we can, but on those free response questions, leave it if you don't need to do anything else with it. So distributing that negative 4 to everything, we've got a negative 12 minus 8x. And then our last step here, since we're on a roll, is to go ahead and subtract that 12. So we got a negative 10 minus 8x over e to the 4x plus 1. Which brings us to integrals, and this is really similar to our natural logs. I think the process is really similar. If we're trying to integrate e to the u du, we're going to end up with e to the u, because it's not going to do anything to it, plus c. And just like with our natural logs, it looks like we didn't have that u prime involved, but remember that that du is u prime. So when you're using u substitution, the u prime gets absorbed into that du, and then we just end up with the integral of e to the u is e to the u. So let's look at some examples. Our first example here, we're going to have the integral of x squared times e to the x cubed dx. Okay, so we're wanting it to look like this form, but anything new that we're doing with integrals, it's all just trying to figure out u substitution, what makes sense, what is still going to show up when we take the derivative of it. So I don't want to choose the whole e to the x cubed to be my u, because then I'm going to have an e to the x cubed in my du, and there's not another one in there. So as far as choosing my u here, the thing that is trapped is my x cubed. And notice that when I take the derivative of my x cubed, I'm going to get an x squared in the derivative. So I've got a 3x squared dx. We're asking ourselves what is missing from that we need to add in, and we're definitely missing that 3. So we're multiplying by our 3 over 3, putting 1 with the x squared, 1 on the outside. So now I have, I just wrote on my shirt. Now we have the whole du here is this 3x squared dx, and then my u here is in the exponent, so I'm going to keep my 1/3 out front. I've got e to u. Everything else gets absorbed into the du. So now I'm just going to be saying that the integral of e to the u is e to the u, always plus c, and then just putting my u back where it goes. So I've got e to the x to the 3rd plus c. All right, let's try another one. So for example 2, we're going to look at the integral of e to the negative x over 1 plus e to the negative x dx. Okay, so a situation where we've got that numerator and denominator, hopefully we're getting a little bit more used to this, but the fact that if I choose my numerator to be u, then it's really difficult to get that du to show up in the right place, because my derivative here of e to the negative x is going to be a negative e to the negative x, but it's a negative e to the negative x in the numerator, and mine is in the denominator. So I want to choose that denominator to be my u. And then for my du, I'm going to have my derivative 1 is 0. My derivative of e to the negative x is going to be an e to the negative x times negative 1 dx. So my whole denominator is the u. My numerator is just missing a negative, so I'm going to multiply my function by 2 negatives. Or a negative 1 over a negative 1, however you want to look at that. So now I can go ahead and take my u substitution. So my denominator was that u, and then my numerator and the dx all got absorbed into the du. So it might help to write it like that. And then I would just have to remember that if I'm integrating 1 over u, I end up with, still going to have my negative, the natural log of the absolute value of u plus c. That was from last week. And I'm just going to put my u back where it goes. So my 1 plus e to the negative x plus c.
Who put that trash can there?